Hello everyone, welcome to all in this video lecture series of Database Management System. I am Deepak Aneja, Assistant Professor, ABES Engineering College, Ghaziabad. Today's in this video, we will cover the topic normalization. These are the content of this video. Today, we will cover the very important topic of database management system is normalization. What are the anomalies in the normalization? Then we will cover the normal forms. In this video, we will cover first normal form and second normal form. So first, what is normalization? The normalization was established by IBM researcher E.F. Code in 1970s. Basically, normalization is a technique to remove or reduce the redundancy, or you can say duplicacy, from a table or a relation. Redundancy in a relation may cause insertion, deletion, and update anomalies. Anomalies are called problems during that are occurred during the duplicacy when we convert the ER diagram into relational model or database design. So it helps to minimize the redundancy in the relation. Normal forms are used to eliminate or reduce the redundancy in the database, or you can say tables. There are two types of redundancy in a table, at row level or second is at column level. First, we will understand the redundancy at row level. To remove the row level redundancy, we use the concept of primary key. Here, we will understand the row level duplicacy by this example. There is a student table where attributes are student ID, student name, age. Here, these are the tuples that are inserted in the table. Roll number 1, student ID is 1, student name is X, age is 20. Second, student ID is 2, student name is Y, and age is 21. Next, this is the duplicate or redundant entry in the row level, in the row level or in the tuple when we insert the row during insert command. So this can be easily removed by defining the student ID as a primary key. Primary key constraint means this attribute is unique or not null. There will be no duplicate entry or not null entry will be inserted. Second, duplicacy or redundancy at the column level. So column level redundancy in a relation may cause insertion, deletion, and update anomalies. Basically, these are DML commands that are used in SQL. Let us understand the concept of anomalies. Suppose this is a student table. Here, the attributes are student ID, student name, course ID, course name, faculty name, and salary. Here, student ID is the primary key. So by defining this primary key constraint, we will remove the row level duplicacy. So all the entries inserted here are unique and not null. Now let us understand the concept of insertion anomaly. Suppose we will insert a new student entry whose student ID is 5, name is X, course ID in which he is enrolled is C1, course name is DBMS, faculty name F1, John, and salary of that faculty is 50,000. That can be easily inserted by the insert command. Now suppose in the college or in the university or in this table, we have to enter a new course whose course ID is C3 and course name is C sharp. Or, or we want to insert a new faculty or a new faculty F3, name XYZ salary 30,000. But we can't insert a new details of course or faculty without student, because student ID is primary key. So the problem occurred during insertion is called insertion anomaly. Now let us understand the concept of deletion anomaly. Deletion anomaly, if we want to delete some student ID, student details whose student ID is 4, we can easily delete by using the command delete table name, where student ID equals to 4. Delete from student where student ID equals to 4. If we have to delete the faculty ID F1, so if we delete the entry of faculty 1, John, entry of John, there will be multiple rows, multiple rows will be deleted that cannot be retrieved in future. So this problem occurred during deletion. This is called deletion anomaly. Now, in update anomaly, if we want to update the student name Aman to Aman Kumar, that is, we can easily update that command, that name, student name Aman to Aman Kumar by using the update command. But if we want to update the faculty 1 salary to 50,000 to 70,000, so the updation will be done at the multiple rows due to update anomaly, duplicacy at the various rows. So this is called update anomaly. Next is normal forms. In DBMS, normal forms are the guidelines that help to ensure the design of the database is efficient, organized, and free from data anomalies. Normal forms help to reduce data redundancy, increase data consistency, and improve database performance. So in DBMS, there are total 5 normal forms. First, first normal form 1NF, second normal form 2NF, third normal form 3NF. This is the advancement of third normal form called BCNF. This is 3.5 normal form. This is called Boy's Code normal form, then 4NF, then 5th NF. Now, let us understand the concept of first normal form. A table or a relation is in 1NF if a table should not contain a multi-valued attribute. Multi-valued attribute means there is a phone number. In the ER diagram, we will represent this multi-valued attribute in double oval. For a student, there may be multiple phone number, or in this example, there is a student table, roll number, student name, and course. One student can be enrolled in multiple courses. So this is the example of student table where roll number 1, student name is X, enrolled in the course C, C++. Roll number 2, Y, name is Y, enrolled in the course Java. Roll number 3, student name is Z, enrolled in the course C, DBMS. This is the wrong representation of a table or a relation. So there can be multiple solutions when to convert this table into 1NF. The solution number 1 is this student roll number, student name, and courses. We will repeat the student roll number and student name with the course C. Then again roll number 1, student name C++, same as with roll number 3, Z, and enrolled in the course C, and roll number 3 name is Jed, enrolled in the course DBMS. However, it is not a good database design as it introduces data redundancy into the relationship. So there is solution number 2. Here we will segregate this attribute course number 1 and course number 2. Roll number, student name, course 1 and course 2. Here roll number 1, student name is X, course number 1 is C, C++. Roll number 2, Y, Java. There is no courses enrolled, only single student Y is enrolled in Java. So here is null value. Roll number 3, Z, student name is Jed and enrolled in the course C, DBMS. This is also not a good database design as there is lots of null values in the table. So this is not a good database design. There may be further solution number 3. We will decompose this relation into two relations, student and enrolled courses. Here we will enter the details of a student. There are 3 students, roll number, student name, 1, 2, 3, and details of the student. And there is enrolled courses, roll number 1, C, roll number 1 also enrolled in C++, roll number 2 enrolled in Java, roll number 3 enrolled in C, and C is DBMS. This is act as a referencing table, or this will act as a base table. Here roll number is primary key, or this roll number act as a foreign key, which will take the reference of student table's primary key. So we can join this table to fetch the data. So this is the better solution. This is a good design as it take care of data redundancy. So next we will move to second normal form. A table or a relation is in 2NF if and only if first table or relation must be in 1NF, or by default our table or a relation is in 1NF when we will create the table into SQL. So by default, when we convert ER diagrams into relational model, the by default the table or relation in 1NF. So the 2NF says the table or relation must be in 1NF, and second, all the non-prime attributes must be fully functionally dependent on candidate key, or there should be no partial dependency. What is this partial dependency? First, we will understand the non-prime attributes. We have already studied in the previous video how to calculate the candidate key. If there is a relation R, A, B, C, D, E are the attributes of a relation R, and candidate key, suppose the candidate key for the relation is AB, then the prime attributes which will include in the candidate key are the prime attributes. A and B are the prime attributes, and non-prime attributes are those attributes which are not the part of candidate key. That is C, D, and E. So for this 2NF, 2NF says the non-prime attributes must be fully functionally dependent on candidate key. So there is a one trick to check this uh, for partial dependency. Partial dependency. That is left hand side should be the in each and every functional dependency, left hand side should be the proper subset of candidate key. And this is logical and right hand side should be the non-prime attribute. This is the condition for partial dependency, or for 2NF we have to check there should be no partial dependency. So this is logical and means this left hand side and right hand side, both true and true will be true, and true and one condition is false, this is false, and one condition is false, then this is false, and both are false, then it is false. So this is in 2NF. If this condition arises, so this is not in 2NF. So this is the condition for partial dependency. So there should be no partial dependency. For example, let us understand this concept with the example. There is a customer table. There is course ID, store ID, and location. Here, in this example, the candidate key is CID and store ID. This is the candidate key combined. Now, you will see this location, this store ID determines location. Location is dependent on store ID. Uh, uh, let us check from this functional dependency. This location is Ghaziabad and its store ID is 1, and here is Ghaziabad and its store ID is 1. Similar with here location is Delhi, its store ID is 3, and here location is Delhi and same store ID is 3. So we can say that store ID determines the location. Let us check, is this table is in 2NF or not. For the store ID determines location. Here we can say, check that this location is the non-prime attribute, as the candidate key is CID store ID. So the prime attributes are CID and store ID, and non-prime attribute is location. So non-prime attribute is partially dependent on store ID. So this is the partial attribute. So this is the partial dependency, because left hand side should be the proper subset of candidate key. Here the candidate key is CID and store ID. So the proper subset of CID and store ID is CID or store ID. So in this case, left hand side is true. This is the proper subset, and right hand side is the non-prime attribute. Yes, this is true. True, true, true. So we will say that here is partial dependency exists. In this table, partial dependency exists. If there is partial dependency, so we can say that the given table is not in 2NF. So what will be the solution? So customer table is not in 2NF. Now, how to make this table in 2NF? For this 2NF, we will decompose the table. Decompose the table in two parts: customer detail and store details. Now, customer detail CID and store ID. This composite key is the candidate key, or here store ID is the primary key. So this uh, will be the primary key. Now we will check here. The candidate key is CID and store ID. Now this is complete the candidate key. So there is no partial dependency. So this table is in 2NF. Now check for this table here. Candidate key is store ID, and store ID determines location. So this is not the proper, this is false, and this is true. This is the candidate key, not the proper subset of candidate key. So the outcome is false. So we can say that the given table is in 2NF. So this is the solution to convert this table into 2NF. Now let us understand this concept through these examples. Let us take a relation R A, B, C, D, E with functional dependency set. This is the given functional dependencies. Let us find the relation is in 2NF or not. So to solve this question, our step number one is to find the candidate key. Here we have already studied how to find out the candidate key. Here we will see the possible candidate key, the missing attributes. B is also in the table, C is also in the table, D is also in the table, we will check the right hand side, E is also in the relation. Missing attribute is A, so we will take the attribute closer of A. So from A we will determine A, and A to B we will determine, B to C will determine, C to D determine, and D to E. So all the attributes are determined by A. So the candidate key is A. There will be no further attributes. Here prime attributes are A, and non-prime attributes are instead of A, there is B, C, D, and E. Now check for each and every functional dependency. As we see here, key candidate key is the single attribute, so there is no possibility of partial dependency, because this is not the combination of two attributes. This is the single attribute. Candidate key is with the single attribute. So as the candidate key is not composite, the case of partial dependencies does not arises in this case. So we can say that the given relation is in 2NF. Let us take one more example. Relation R, attributes are A, B, C, D with functional dependency set as A, B, C, D, C, A, D, B. Let us find this relation is in 2NF or not. So first of all, we will find out the candidate key. Here, the right hand side, all the attributes C, D, A, B are in the relation. So we have to try the hit and trial method. Combination A, B, C, and D. Take the closure set. A, no, we cannot determine further. B, from B we cannot determine further. From C we determine A, or from AC we cannot determine further. The closure set of D we can determine D to B, and we cannot determine further. Now we have to make the combination of two attributes AB, AC, AD, then BC, BD, and CD. Now take the attribute closure of this AB to AB, then AB to CD. The first candidate key is AB. We have determined all the attributes of the relation. The first candidate key is AB. Next, try for AC. AC, from AC, C to determine A is already the part of this attribute closure. We cannot further determine. Now AD, AD from D to B, and AB to CD. Now this is one more candidate key, AD. Now check for BC, BC, C to A. Now AB we can determine CD. This is another candidate key, BC. And now check for BD, from D to B, and there is no further. So this will be not the part of candidate key. Now CD, from C to A, and then D to B. So CD is another attribute. There is no further combination. So this is the candidate key. Now the prime attributes are A, B, C, and D. Non-prime attributes are null. There is no non-prime attributes. So if we check for the right hand side, the right hand side is always false, as there is no non-prime attribute. So we have composite candidate key, but no non-prime attribute. So the case of partial dependency does not arises. So we can say that this relation is in 2NF. Now let us understand one more example. Let's take a relation R A, B, C, D, E, F with the FD set. C, F, E determines A, E, C determine D, and A determine B. Let us find this relation is in 2NF or not. So first of all, we will find out the candidate key, step number 1. So candidate key, for candidate key, we have to check for the missing attributes. F is already in the A, D, and B. Missing element attributes are C and E. Let us take the attribute closure of CE. So CE, from C we will determine F, from E we will determine A, from EC we will determine D, and from A we will determine B. So all the attributes we can determine through CE. So candidate key is CE. There will be no further candidate key because the missing attributes already determine all the attributes of the relation R. So the prime attributes are C, E, and non-prime attributes are A, B, C, D, and F. Now check for 2NF. So we will check for 2NF. Here is C determines F, E determines A. We have to check for each and every functional dependency, given functional dependency. If any of the functional dependency is not in T2NF, then we can say that the given relation is not in 2NF. So check for this. Our condition to check is left hand side should be the proper subset of candidate key, and right hand side should be the non-prime attribute. Now check for this. C is the proper subset. Yes, this is true because candidate key is CE. The proper subset of CE is C, either C or E. So here is C true, and right hand side is F. F is our known prime attribute, true. So true. So this is the case for partial dependency, or for 2NF there should be no partial dependency. So this functional dependency is not in 2NF. So from this partial dependency, we can say that the whole relation is not in 2NF. Let us check for further functional dependency. Is it in 2NF or not? Let us check. E is also the proper subset, and A is the non-prime attribute, true. So this is true. This is partial dependency, or there should be no partial dependency. So this is not in 2NF. So this is also not in 2NF. Now check for this EC. EC is the proper subset, false, because it is the candidate key. So we have to check for the proper subset. So this is false. And if one condition is false, the outcome is also false. Now let us check for D. D is non-prime attribute, true. False and true is false. So this is no partial dependency. So this functional dependency is in 2NF. Now check for A, B. A is the proper subset, false, because there is candidate key is C. The proper subset is either C or E, but here is A, so this is false. And B. B is non-prime attribute, true. The outcome is false. There is no partial dependency, so this is in 2NF. But these two functional dependencies not in 2NF. So we can say that this relation is not in 2NF. I hope you will understand this concept of 2NF, second normal form. These are the references. Thanks for watching this video.